So this was a weekly homework which was related to bonding structures and shapes. The first 68 questions I have already solved. So we'll do from 69. So we'll solve from question 69. Predict whether the lattice energy of magnesium oxide is more or less exothermic than the lattice energy of magnesium sulfide. Justify your answer in terms of size and the charges of the ions involved. Look, on what factor the lattice energy depends on? The lattice energy depends on the strength of ionic bond. And the strength of ionic bond or the lattice energy, to have a high lattice energy or more exothermic, the size of the ions should be small as possible. And the charge on the ions should be large as possible. So large charge and small size result in a higher value of a lattice energy. So when we talk about magnesium oxide, like magnesium ion is there. So magnesium ion, first shell, it will have 2 electrons. Second shell, it will have 8 electrons. It's a magnesium ion, so it has lost 2 electrons. So 2 shells are there, this will be plus 2. And when we talk about oxygen, oxygen is 2,6, but oxide ion will be 2,8, and it took 2 electrons from magnesium. So it will be minus 2. This is a magnesium oxide. When we talk about magnesium sulfide, the magnesium will be same. Like the first shell, it will have 2 electrons. And the second shell, it will have 8 electrons. But when we talk about the sulfur, sulfur is 286. Like sulfur atom is having 3 shells. And when it take 2 more extra electrons, so the configuration changes to 288. So first shell 2, second shell 8, and the third shell also 8. So first shell 2 electrons, sulfur, second shell 8 electron for sulfur, the third shell 6 electron for sulfur, but 2 extra electron it took from magnesium. So this is magnesium sulfide. Now, which one we expect to have a higher value of a lattice energy or will have a stronger attraction? Because the lattice energy depends on the size of the ions, and we want the size of the ion should be small as possible, and the charge on the ion should be large as possible. So, but in this case, the charge is same, like magnesium is plus 2, oxygen minus 2. Same thing, magnesium plus 2, and this magnesium is plus 2. And sulfur is minus 2. So the size, the charge on the ion is same. There is no difference. But the charge on the ion is the charge on the ion is same, but the size is different. So charge will not affect. So which one we expect to have a higher lattice energy? So we expect that magnesium oxide will have a higher lattice energy or more exothermic as compared to magnesium sulfide. What is the reason for that? The things you will mention, like first point, you will mention the lattice energy depends on the size of the ions and the charge on the ions. That is the first point. Then you will mention magnesium oxide is more exothermic compared to magnesium sulfide. What is the reason? The third mark you will mention that because oxide ion are smaller in size as compared to that of sulfide ion. So as a result, there will be stronger electrostatic attraction between magnesium and oxide ion compared to magnesium and sulfide ion. Is it clear? The points which we'll use. About the lattice energy. But when we talk about like the same, if the same question was there, which one will have a greater difference in the practical value and the theoretical value of the lattice energy, then magnesium sulfide will have a greater difference as compared to magnesium oxide. Because magnesium sulfide the distortion of polarization depends on the size of a negative ion. It should be large size and it should have a greater charge. So as a result, what will happen? Magnesium sulfur will have greater distortion. So it will have a greater difference between the theoretical and the practical lattice energy. But the lattice energy of magnesium oxide, when we talk about the lattice energy of magnesium oxide, maybe if it is minus 900, this will have a lattice energy of minus 400. But the theoretical, this is example theoretical value, practical value a bit higher, maybe 900 and say 12. But for this one, the practical value will have a greater difference with the theoretical value. So if this was minus 400, this will be minus 440 or 430 or 50, any number, but it will have a greater difference. So difference in the lattice energy depends on polarization or distortion. And the strength of ionic bond or the melting point totally depends on the size of the ion should be small and the charge on the ion should be large. In question 70, the lattice energy of sodium fluoride, sodium chloride, and magnesium fluoride are there in the table. You can clearly see the magnesium fluoride is much higher than sodium fluoride and sodium chloride. Explain in terms of size and the charges, the ions involved, the difference between the lattice energy of sodium fluoride and sodium chloride. So when we talk about the sodium chloride, like the sodium ion, the configuration will be 2,8. And fluoride ion, the configuration will be 2,8. When we talk about sodium chloride, so sodium will be 2,8, but the chloride ion, it will be 2, 8, and 8. So this will have more shells. So this is having only 2 shells. This will also have 2 shells. This will have 2 shells, but the chlorine will have 3 shells. So the lattice energy depends on the size of the ion should be small and the charge on the ion should be large. In this case, both have the same charge, but the size of the ion for a fluorine is smaller as compared to size of the ion chloride ion. So the fluoride ion will have a greater attraction. As a result of a greater attraction, the lattice energy of sodium fluoride will be higher. So you'll mention one point is mentioning the fluoride ion is smaller than chloride ion, or you can also mention fluoride ion will have a larger charge density because small volume, more charge. Like same charge in a small volume, so the charge density will be higher. And the second point you will score by mentioning that fluoride ions have a stronger electrostatic attraction, or there's a strong electrostatic attraction between sodium fluoride and fluoride ion compared to sodium and chloride ion. As a result, the lattice energy will be higher. Then sodium fluoride and magnesium fluoride. So here the difference is not because of the size, the difference is because of the charge. So sodium ion is there, the configuration of a sodium ion is 2,8. And for fluoride, the configuration is 2,8 as well. Magnesium fluoride 2,8 and 2 fluoride, so 2,8, another fluorine is there also 2,8. So they all have the same size of the second shell is used. Electrons from the second shell are used, so they are in the same size. But why still the magnesium is having a higher lattice energy, magnesium fluoride is having a higher lattice energy as compared to sodium fluoride? So the result is because, and as a result, what will happen? The magnesium ion, because in case of a magnesium ion, even though the shells are same, 2,8 and 2,8, the shells are the same. But what difference is there? Sodium is having 11 protons, where magnesium is having 12 protons. So 12 protons are attracting those 10 electrons. Here 11 protons are attracting the 10 electrons. So as a result, the magnesium plus 2 ion will be smaller than sodium. And when the magnesium plus 2 ion is small, and it has a greater charge as well. So 2 points will mention. One thing, the magnesium plus 2 is smaller than sodium plus 1. Why it is smaller? Because it has a greater number of protons in the nucleus, so stronger attraction towards the electron. And the second mark is the magnesium plus 2 is having a greater charge compared to sodium, which is plus 1. So at both leads to smaller size and a greater charge, stronger attraction. That's why it will have a higher lattice energy. Then draw a diagram to show the region of electron density in both parts of a double bond between carbon atoms in ethene and label each region with appropriate symbol. Like here we have to draw how the region of finding electron is maximum or electron density cloud, or simply we have to show the sigma and the pi bonds between the carbon atoms. So in short, we have to show a sigma and pi bond. So how we can represent, and it's ethene. Ethene means like between the carbon atom, there's a double bond. And yesterday I explained whenever there's a double bond, one of the bond is sigma, another bond is pi. So how we can represent or how we can show the sigma and the pi bonds here? But only we need draw a diagram to show a region of electron density, means the orbital in both parts of a carbon, in both parts of double bond between carbon atoms. So carbon atoms we have to show. So if this is like example px, this is also p. So what will happen? There will be a complete overlapping. As a result of a complete overlapping, which bond it will form? It will form a sigma bond. And then one of the axis in y-axis is there, or so there will be attraction from top and from bottom as well. And as a result of this attraction, there will be a pi bond. So you have to show a sigma and the pi bond between the two carbon atoms. Is it clear? This is the same thing we did yesterday. If there was another, like a similar question was there, and if they say about ethene or ethine, sorry, ethene is already there. If there was ethine, ethine means between the carbon and carbon, there's a triple bond. And when there's a triple bond, two of them are pi and one is a sigma. Any one of them is a sigma, two of them are pi. So how to represent one sigma and two pi? So when we draw the structure, like this is one and this is another. So because there's a complete overlapping, so this will be a sigma bond. Then this is y-axis. This one is also y-axis. So there will be a pi. And then for z-axis, like this is z-axis. This one is also in a z. And there will be attraction between them. That's also pi. So there will be one sigma and two pi if there's a triple bond. But in the question, we have double bond. That's why for a double bond, we represent one is a sigma covalent bond. Another one is pi covalent bond. There is attraction from the top and the bottom both, and that is refers to a pi bond. In question 72, most solids exist as a lattice structure. Complete a table using a tick or a if the substance conduct, and or a cross if the substance does not conduct. If we have a sodium, a metal is there in a solid state. So you can use screen annotation to complete this. If a metal is there in a solid state, does it conduct electricity? Yes or no? If it is yes, tick. If it is no, cross. You can annotate on the screen. So yes, so solid sodium does not, but sodium oxide can. not like solid sodium can, but sodium oxide is an ionic compound, cannot. In liquid or a molten state, yes, it will conduct. Explain the electrical conductivity of a sodium and sodium oxide in the solid and the liquid state. So what are the points you will mention in a solid sodium metal? There are free or a delocalized electron, so it can conduct and even in a liquid state, there are free localized electron. But in sodium oxide, in solid state, there are no free electrons or ions. But in molten state, the ions are free to move. So solid and liquid sodium conduct due to free electrons or delocalized electrons, or electrons are free to move. But molten, like solid sodium oxide, does not conduct because ions are not free to move. And why the liquid or a molten can conduct? So solid sodium oxide does not conduct. But if we have a liquid or a molten sodium oxide, because the ions are free to. So these are the points you will mention. Then the diagram shows a sulfur dioxide may be drawn to represent as shown. Whenever there's an arrow, it means there's a dative bond. Complete a dot and cross diagram. A molecule of a sulfur dioxide. Only show the outer electrons. There's a double bond if there's a double bond. And use dot to represent oxygen and cross for sulfur. So this is oxygen, then sulfur, oxygen and sulfur. Because there are two lines, it means two pair of electrons are there between the oxygen and the sulfur, or a double bond is there. And on oxygen, there will be six unshared. This oxygen belongs to group 6, so it's shared 2, so 4 unshared electron will be there. Sulfur also belongs to group 6, so it will have like 1, 2, 3, 4. But those remaining two more, they are used like the lone pair of a sulfur is given to oxygen, so the electrons of sulfur will be there as forming a dative bond. Dative bond means when both electrons involved in the sharing are coming from the same atom. And then for oxygen, 1, 2, 3, 4, 5, 6. So this oxygen is stable. How it is stable? 1, 2, 3, 4, 5, 6, 7, 8. So oxygen is stable. What about sulfur? 1, 2, 3, 4, 5, 6, 7, 8. It's also stable. And what about the other oxygen? That is also stable. This is how the sulfur dioxide structure looks like. Which molecule is a polar? Polar molecule means like it depends on the bonds, and it also depends on the geometry, polarity of a molecule. So how we identify? Look, BeCl2. In this case, it's a linear structure, and both chlorine have the same tendency to attract the electron. So as a result, what will happen? They cancel out the effect of each other. Carbon dioxide, so carbon is there bonded with two oxygen. Each oxygen is more electronegative than carbon. So each oxygen will attract the bonded pair, but they cancel out the effect of each other because it's a linear structure. In CH4, carbon bonded with 4 hydrogen tetrahedral structure again. Each is having the same tendency to attract. So as a result, they cancel out. Like carbon is more electronegative, but they have a very small difference in the electronegativity. So usually carbon hydrogen bonds are non-polar bond, but they cancel out each other as a symmetry is there. But in case of hydrogen sulfide, there are two bond pair and there are two lone pair. As a result, it will have a bend or a V shape. And because like these two hydrogens are not able to, like the sulfur, it does not cancel out because it's not a linear structure. If it was a linear structure, then they completely cancel out the effect of each other and the molecule will appear as a non-polar. Polar molecules are are affected by the external electric field, but non-polar molecules are not. That's why D is the right answer. So linear or tetrahedral structures, if their identical atoms are attached, then it will be a non-polar. But if we have a bend or a V shape, even identical atoms are attached, but it will be a polar molecule. So the geometry of the molecule also affects its polarity. And that we'll discuss in detail. Unit 2, this topic is there in detail. Unit 2, we just discussed the geometries in this one, but in Unit 2, you will learn how to predict the molecule from the geometry. This question is about the structure of a substance NH4. We have to predict the bond angle in NH4. First, what is NH4? Nitrogen, like ammonia is NH3. And there's a lone pair on nitrogen, and this lone pair on nitrogen, the proton is attracted and there's a dative bond. So when you're predicting a geometry, the dative bond you will also consider as a covalent bond. So 1, 2, 3, and 4 covalent bonds are there. If we have 4 covalent bond and there is no lone pair, then what will be the structure? The structure will be tetrahedral, and tetrahedral will have a bond angle of 109.5. What about H3O? So when we talk about like water molecule, H2O, it is bent or V shape. But H3O means there is another dative bond, like hydrogen is attached here. There's a dative bond. So how many bond pairs are there? 1, 2, and 3. So 3 bond pairs and 1 lone pair. So 3 bond pair and 1 lone pair, it will be trigonal planar. And when it is trigonal planar, the bond angle will be 107 degree. So whenever you're predicting a geometry of a molecule, the dative bonds, you will consider them as same as like a simple covalent bond when predicting a geometry. The next is the BF3 and PH3 molecule. Name the shape. So boron trifluoride. Boron does not have any lone pair on the central atom, but in phosphorus belongs to group 5. So it has the lone pair. So when we have 3 bond pair and we have 1 lone pair, what will be the geometry? It will be trigonal planar. And this will be trigonal. What will the bond angle? The bond angle is 120. And what will the bond angle? It will be 107. So name the shape of BF3 and PH3 molecule and explain why they are different. So why the molecules are different, you will relate. First thing, 1 mark you'll get when you mention BF3 is trigonal, planar, or trigonal. And this will be trigonal pyramidal. Sorry, not planar, pyramidal. This was planar. Because when 3 bond pair, 1 lone pair, trigonal pyramidal. And when only 3 bond pair, no lone pair, then trigonal planar. So this will be trigonal pyramidal. So 1 mark is for mentioning trigonal planar, 1 mark is for trigonal pyramidal for PH3. And reason is that you'll mention in PH3 there are 3 bond pair and 1 lone pair, where in BF3 there are 3 bond pairs. And the another thing you'll mention, the lone pair repulsion is more than the bond pair repulsion. As a result, the bond angle will decrease more. Then explain with reference to the structure and a bonding in each substance why electrical conductivity of a graphite is 1 into 10 to the power 5, but the diamond is 1 into 10 to the power minus 2. Like why graphite is a better conductor? then diamond. And 4 mark questions. So points you should keep in mind whenever you are comparing the structure of diamond and graphite. First thing you'll compare that they both have the giant structure, but in diamond it has a diamond. Each carbon form three covalent bond, and there is one electron delocalized. But in graphite, each carbon atom form three covalent bond and one delocalized. Where in diamond, all the electrons in the diamond are involved in the bonding. And graphite is having a layer structure, so electron can flow between these layers. Where diamond graphite is having a layer structure, but diamond is not having a layer structure. So both are giant structures. And graphite, each carbon, the layer and hexagonal structure, where diamond is tetrahedral. Then in graphite, three electrons are involved in the bonding, and there is one free electron. Where in diamond, all four electrons are involved in the bonding, and there is no free electron. That's why the diamond cannot conduct, or a very low rate it conduct as compared to that of graphite. And explain why the chlorine bond length is 0.19 nanometer, where iodine is like, why the chlorine bond length is shorter than iodine. Because then it totally depends on the number of the shells. Like iodine, there are more shells as compared to that of chlorine. And as a result, there will be less attraction between the nucleus and the bond pair. And in iodine, there will be a greater shielding effect. So in iodine, more shells. When we have more shells, there will be a greater shielding. And there is a greater shielding. As a result, there will be a weak attraction to the bonded electrons. And when there's a weak attraction to the bonded electrons, the bond length will be longer. Like the distance between the nucleus from one nucleus to another, that will be much longer. And you can say other way around, you can say chlorine is having less shells, less shielding effect, stronger attraction to the bonded electrons as a result, or between the nucleus